Let's talk about some definitions that we use in probability and statistics. The first one is random variables. So what is random variables? Variables whose values are uncertain is called random variable. Okay, this means variable whose values cannot be known in advance until it actually takes on a particular value. Okay, so instead of forecasting the random value, for example, rainfall is going to be 10 millimeter. Instead of doing that, we attach a probability with the random value. So when there is a randomness, when we understand there is a randomness in the outcome, we attach a probability, such as 30% chance of 80 millimeter rain, okay, or 40% chance of 70 millimeter rain, and so on. So what are the random variables in hydrology? Stream flow, rainfall, soil moisture content, all are random variables. Similarly, evaporation, evapotranspiration, groundwater table, all of them are random variables. And how we denote these random variables? Mathematically, we denote them by these uppercase letter X, Y, Z, right? So uppercase letter denotes a random variable. So that this X means rainfall depth. It doesn't, it's not about the value, but what is the variable. So X means depth of rainfall. Y means stream flow or evaporation or evapotranspiration, soil moisture. Okay, so these means some variable, and the lowercase letter uh, is used to denote the value of that random variable. So X equals 40 millimeter means rainfall depth is 40 millimeter. Y equals 30 meter cube per second. That means the random value takes Y equals to 30 meter cube per second. Now, when the random variable X equals to 40 millimeter, that means that is an event. So there is a difference when the small letter X equals to 40 millimeter, that is the value of the random variable, whereas when the X equals to 40, the capital X equals to 40 means that is a particular event. Okay, so we are talking about when X becomes 40 or when Y becomes 70. Okay. Similarly, the random variable can have a range. So rainfall being between 10 and 30 millimeter, or the event being 30 meter cube per second or more. Okay, when the stream flow, we are interested in the event or the stream flow being 30 meter cube per second or more. So some random variables can take only discrete values, and some can take continuous values as well. Okay, so there are different kind of variables, and some random variables can take discrete values, so 1, 2, so no in betweens, whereas continuous value can take continuous value between the 2 points, okay, which can be minus infinity to plus infinity or anything in between. Now, discrete random variable can assume a value from a finite number of a set. Okay, so for example, number of days in a month, sorry, number of rainy days in a month. It can be 0 days, it can be 1, it can be up to 31 days. So you cannot have 20.5 number of rainy days, right? So you can have either 24 or 25. So so these kind of variables can take only finite numbers within a set, and that is called the discrete random variables. Whereas there are other variables which can take infinite number of values. For example, river flow, it can take 1 meter cube per second, 2 meter cube per second, 2.1, 2.15, 3.7, 3.771, 7775, 777775, or so on, right? So there are infinite number of values in between, and if the variable can take infinite number of values, then it is called continuous random variable. Now, most of the variables in hydrology are continuous random variable, but there are also some discrete random variables. And once we know whether a random variable is a discrete random variable or continuous random variable, then we can assign associated probabilities to them using mass probability function or mass density function. So random variable, discrete random variables, we have mass probability function, and continuous random variable, we use mass density function. Recurrence interval or return period and the annual exceedance probability P. So they are linked together. The annual exceedance probability, that is percentage of chance of being equaled or exceed in any given year. So it can be rainfall. So rainfall being 100 millimeter or more, or it can be a stream flow being 50 meter cube per second or more, right? So annual exceedance probability in any given year is defined by P, and that equals to the return period. So return period is the expected time to wait for the next event. So in an average, how frequent that event occurs. Okay, so that's important. Is in an average. That doesn't mean that will happen every t number of years, but in an average that happens. If you look at the historical data, that event happens only uh, every t years, right? But as I said, it has been very confusing to many people that if it is 100-year return period flood, people think that it will happen only after 100 years, which is not the case. It can happen next year and the year after as well. But if you have the 100-year return period flood, then the annual exceedance probability of that flood is 1 over t, which is 0.1. So that 100-year flood can happen in any given year with the probability of 1%. Okay, it can happen in any given year with 1%. So that's called annual exceedance probability. So the relationship of T and P is T equals to 1 divided by P, or P equals to 1 divided by T. Okay, so annual exceedance probability and the recurrence interval. Now, the other term is the reliability. Okay, reliability of our structures, right? We have these based on hydrology. We take the flood of 100-year magnitude, or 100-year return period, or 50-year return period. We decide, but we want to know the probability of that flood will not occur in the lifetime of our structure. Maybe if your structure is 10 years period, if you design your structure for 10 years period, what is the probability that the flood will not occur in 10 years or 50 years or even 100 years? Okay, so we can calculate, and that is called reliability, and which is 1 minus 1 divided by t to the power n. And the risk, that means the opposite of reliability is the risk. That means probability that flood will occur at least once in that lifetime of the structure. Okay, lifetime of the structure, n can be 10 years, 50 years, which can be more than the return period, which can be less than the return period. So it has no direct relationship with the return period. You decide your return period based on the historical data of your random variable, and then you decide the structure use of the structure. So for how many years you want that structure to use, and based on that you decide the end year. Okay, and from there we can calculate what is the risk. Okay, probability of the flood occurring at least once is 1 minus reliability, which is 1 minus 1 minus t to 1 by t to the power n. Now let's talk about the discrete random variables. Let's say we have 3 coins. Okay, we are going to toss three coins one at a time. And what are the outcomes? How we calculate the probability? First, we calculate what are the potential outcomes, right? So when we toss the first coin, you have head and tail, right? And what is the next? So when you throw the first coin, you may get head, you may get tail, and when you throw the second coin, then if you have got the head in the first, you may get head or tail, and if you have got tail first, then also you may get head and tail. What happens if you throw the third coin, right? And here also, if you have got head in the second, you may get head and tail in the second coin, head and tail, and so on, right? So these are the possible outcomes. So you may get three heads, head, head, head. You may get head, head, and tail, head, tail, head, and so on. So these all are the possible outcomes. So from here we can calculate what are the probabilities. So what is the probability of getting all three heads? What is the probability of getting only one head? Or what is the probability of getting first head and two tails, right? So we can calculate all these different probabilities. So what are the number of total outcomes? Eight, right? So 1, 2, 3, 4, 5, 6, 7, 8. You have 8 outcomes. And what is the probability of getting all three heads? That means only one. So 1 over 8. What is the probability of getting all tails? Again, 1 over 8, right? What is the probability of getting two heads? What is the probability of getting two tails? And so those kind of things you can calculate. Now, if you tabulate that outcome here, so three heads, head, tail, and so on. So what you get, this is the outcome. Now, first we define our random variables. What is our objectives? What we are looking for? We may be looking for getting head. Okay, what is the probability of getting head? Or we may be looking for getting tail. So you can define your random variable what you are looking for. Let's say we are looking for getting head, and that is the random variable. Getting head is the random variable, and x is what we denote to define that random variable. Okay, so x is getting head, and what are the values of the random variable? So we can get 0 because no head. If there is no heads, then you can have 0 as a random variable, 1 one head, 2 as two head, and all three are three heads. So you can have four different outcomes, right? So you can have 0 head, 1 head, 2 heads, and 3 heads, right? 0 heads, 1 head, 2 heads, and 3 heads. So these are the possible outcomes. So you can have only four discrete outcomes, right? So we can tabulate this in this form. So when x equals to 0, probability is 1 over 8. X equals to 1, 3 over 8. So x equals to 2, 3 over 8, and x equals to 3, 1 over 8. Okay, so these are the four different outcomes, and the probability is 1 by 8, 3 by 8, 3 by 8, and 1 by 8. And the total of the all probability has to be 1, right? So this is called the probability distribution of table. So probability of different occurrence. So this is for a very simple case, but we can extend it for a much more complex example. Now, a little bit complex. You have the two dices. You throw two dices and see what are the combinations of the values you get. Okay, summation of the values you get. If it is 4 and 2, it becomes 6, right? So similarly, what are the values? So if you throw and you get 1 and 1, that is one combination, right? So you get the summation as 2, and there is only one possibility. You get in both red and black dice, you need to get 1 to get sum as 2, right? If to get 3, you have 1, 1 and 2, and 2 and 1. So these are the two possibilities. Similarly, to get 7, you have number of different possibilities. So you get 1 and 6, 6 and 1, 2 and 5, 5 and 2, 3 and 4, and 4 and 3. So all these are possibilities. So that means to get sum, you have one combination. To get 3, you have two combinations. To get 7, 6 combinations, and so on. So based on this, you have like total numbers, what total possible outcomes. So that is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, right? Some of the numbers, the random value variable is some of the numbers, and the value of the random variables is from 2 to 12, right? There are 11 possible outcomes, and the probability of each outcome is what we tabulate here. Probability of getting 2 is 1 out of 36, right? So if you sum them up, there are 36 different possibilities, and out of that 37, getting 2 is only 1, right? So 1 out of 36. Whereas a possibility of getting 7 is, you have 6 different combinations, so 6 out of 36, which is 1 by 6, right? And the variable and the probability will give us the probability distribution. Now we can write that same probability in this tabulation in the form of table or in the form of the graph. Okay, because this is the discrete probability, because it takes only random variable, but from the finite sets, this is called the probability mass function. Okay, and if you sum the probabilities and add them up, that we get the cumulative probability. Okay, that means getting 2 is 1 over 36, getting 2 and 3 is 3 over 36, getting 2, 3 and 4 is 6 over 36, getting 2, 3, 4, 5 is 10 over 36. So you can define this as, what is the probability of getting the sum as 5 or less? What is the probability of getting sum as 7 or less? What is the probability of getting 11 or less? Okay, so that is the cumulative distribution function, to get the value up to that point or less. So that is defined as a cumulative probability. So from, you can have this probability mass function for the finite elements. Okay, for the discrete random variables, you have the probability mass functions, and you can also plot the cumulative probability. Okay, so you can have a plot, or you can have a table. Okay, so these tables or these curves define the relationship between the outcome of the random process and the probability of occurrence of that random variable outcome. Okay, so this is the outcome. Outcome is 7, and the value of the cumulative value is 0.5 something, right? Similarly, what is the probability of getting 9 or less? And you can read from here. Whereas if you read this probability mass function, you can directly read what is the probability of getting 6. Probability of getting 6 is 0.14. What is the probability of getting 2 is 0.03, right? So you can, from the probability mass function, you can directly get the probability of that particular event, whereas from cumulative distribution function, you can get the probability of up to that point. But summation of all the probability should be equal to 1. So that is important. Sum of the probability has to be 1. Now probability of xi as probability of x equal to xi for discrete random variable. So how we calculate this? probability of this p probability of x being equal to xi. That means this random variable, which is sum, being equal to 6 is the probability of xi. So that means probability of this getting 6 equals to pxi, which is 0.14. Whereas when we talk about the using this cumulative distribution function, what is the probability of x equals to xi? What we do, probability of x I minus probability of xi minus 1. So this is because this is the cumulative probability. So this minus this gives the probability of xi. So sometimes you use probability mass function, sometimes you use cumulative distribution function, but you can calculate the probability using either of them. Now this is an example. Okay, so you have the continuous variable like flood data, and what you can do, you can convert the continuous data also in discrete form. It's not necessary, but sometimes if you require, you can do that. So this is an example of gauge height in Rockhampton Station. Okay, so you have the number of data from 1860 to 2000 something, and this gives the water level, okay, at the Rockhampton Station. Now you can divide this in number of groups. So okay, so 3 to 4, 4 to 5, 5 to 6, 6 to 7, 7 to 8, 8 to 9, 9 to 10, and 10 and above. So you divide in multiple groups, and you just count how many events are there. So 3 to 4, 0, 4 to 5, 5 events, 5 to 6, 13 events, and similarly 9 to 10, 3 events. Okay, so you have 1, 1, 2, 3, 9 to 10 events, and maybe more than 10, probably one event, right? So it has to be one, and you can calculate the probability of the group and the cumulative probability as well. Okay, and then we can calculate the probability mass function, and you can also calculate the cumulative distribution. Okay, cumulative probability distribution, as I showed before. Now there are many hydrological variables that doesn't take the random, and it is not necessary for all the continuous variables to convert in discrete variable. Okay, there are many variables which are not discrete, and we can, if there are discrete variable, if there are continuous variables, you can convert them in a discrete form. So you can define the range and then count the number of the values within that range, and you can convert that in discrete form, but that is not necessary. Okay, because we have the uh, probability distribution for continuous variable as well. So this is an example. Here, this is called the probability distribution function. Not probability mass function. So that is important difference. In continuous probability, we use probability distribution, probability density function. Okay. In continuous probability variable, we use probability density function, whereas for discrete variable we use probability mass function. Now the concept, however, is the same, right? If the concept is same, this value gives the probability of for example, if what is the probability of the value being 2 to 1, you can calculate the area under this curve. Okay, so area under this curve will give you the probability of the value between these two ranges. And you can also plot this cumulative distribution curve using this cumulative distribution function. You can calculate what is the probability of the random variable being, um, I'm not sure here, like maybe 1.3. Okay, so 1.3 or less, or what is the random the probability the random variable being 0.7 or less. Okay, so you can calculate using the cumulative distribution function or probability distribution function. The area under this probability, sorry, not distribution, okay, probability density function, the area under this probability density function always has to be 1, right? So cumulative shows this is 1, but here the area under this should be equal to 1. So what is the probability distribution function? What is the requirement of the probability distribution function? Any function whose value is not negative, okay, any function whose value is not negative, and the area under the curve is exactly 1 can be PDF. So there is no any kind of function. So fx equals to x square, or fx equals to x cube minus 3x divided by 2, whatever the function is. If the value of the function is not negative, because we know there should be no negative probability. So if the value of the function is not negative for any value of x, and the area under the curve is 1, then that can be the probability density function. Now, one thing important to know is this PDF or probability density function is not the probability. So if you look at here and then you see this is 0, and then you read here the probability of x taking 0 is not equals to 0.4, right? Because there are so many values in between. So technically, so there are just how many, let's say if the probability ranges from -3 to 3, so how many values it can take within that? It can take infinite number of values, right? So it can be 0, 0.1, 0.01, 0.001, 0.0001. So there are infinite number of values, and based on our definition, the number of outcomes are infinite, and getting that one particular value is 1 over infinite, right? So which means the probability is 0. So in the cumulative probability, we don't talk about the, sorry, in the continuous probability, continuous random variable, we don't talk about getting one particular value of the random variable. What is the probability of x equals to 0? We don't talk like that. What we say is, what is the probability of x is less than 0, or x is more than 0, or x is between 0 and 1, 0 and -1, 2 and 3. Okay, we talk about the range, or less than something or more than something. Okay, we don't talk about one particular value, because the probability of one particular value, any particular value, is by definition is 0. All right. So when, if we ask like what is the probability of the flood being, or the stream flow being 10.395 meter cube per second, that is 0, because that 10.395 is only one of the possible outcome out of infinite number of possible outcomes, right? So that means probability becomes 1 over infinity, which is 0. So that's why we talk about the probability of that random variable less than a particle value a, or between some value, or greater than some value, and so on. Now, so we identify the region, and we integrate the PDF over this region to obtain the associated probability. So let's say we want to find out what is the probability of the x being less than or equal to a. Okay, so this is a, so the x, this is a random variable x, the value of the random variable x, and this is the value a. So what is the probability of this being less than a, right? And that is the integration. This is what we call the area, right? So probability is area under this probability density function. And how we calculate that area? We integrate from minus infinity or whatever the lower range is up to that point, okay? And then integration of this curve is the cumulative probability. So minus infinity to a fx dx. And what is the exceedance probability? Exceedance probability is the opposite of the cumulative probability, right? So total probability has to be 1. So cumulative probability is this infinity. That means exceedance probability is again the area under this curve, which is from a to plus infinity fx dx, right? So a to plus infinity here, a to plus infinity, and the area under this curve, which is equal to 1 minus area under this the left hand side, okay? So instead of integrating right hand side, what we do is we calculate the probability, uh, we calculate the cumulative probability up to that point. So x value being less than or equal to that particular value, and then we subtract that value from 1 and we get the exceedance probability. So in hydrology, we want the exceedance probability. What is uh, the probability of stream flow being more than 50 meter cube per second, or what is the probability the gauge height being more than 7 meter, or like that, okay? So that is what we want in hydrology. For flood rainfall, we want the exceedance probability, right? So that's how we calculate exceedance probability. We calculate the cumulative probability using the cumulative uh, distribution function, using the probability or using the probability density function, and then we calculate the exceedance probability, okay? So exceedance probability is 1 minus exceedance probability is 1 minus cumulative probability, okay? That's one important point. And for some reason, if you want to find the probability within the range, if the what is the probability of the random variable being between b and c points, these 3 points, then we calculate this area and we integrate the range, okay? Again, b to c fx dx, but it is easier to calculate the cumulative probability. That's why we calculate minus infinity to c, and then we calculate minus infinity to b, and we subtract from the first to second, and we get the probability of the range. So when using cumulative probability curve, probability of x taking on value less or equal to a, or cumulative probability is x equals to a. So if we want to use the probability, sorry, this cumulative probability curve, then probability of x equals to a is probability of x is less or equal to a, okay? So cumulative probability of x equals to a means probability of x, all these the area under this curve, okay? So cumulative probability, if you read the probability cumulative probability curve, this value actually means the area under this curve, okay? From minus infinity to this whatever a value is up to that point, you calculate the area, and that is the cumulative probability. And exceedance probability is 1 minus fa, okay? So that's how you calculate if you use the cumulative probability. So in all the probability distributions, there are you will always have two things. One is the probability density function and the cumulative probability function, okay? So or cumulative distribution function. So you can use either, and using that you can calculate the probability. So, but you need to be careful which one you are using.